Hi everyone, this is going to be our introduction to graphing inverse trig functions. And on our note-taking sheet, we see that we have three columns, one for each trig function. So let's get started with sine. To start our conversation about sine, we're first going to just remember what this looks like from 0 to 2 pi. So sine always starts at 0. It's going to come back down to the midline, which in this case is our x-axis, come down to the low, back up to the midline. And we want to be careful that we don't make it look pointy. Nice curve. And then heading the other way goes down to the low, back up to the midline, which in this case is our x-axis, up to the high, and back down to the x-axis. And in that class, we discussed how technically this does keep going forever and ever in both directions. And we also talked about how, even though this passes the vertical line test, which is great, in its current form, negative infinity to infinity for a domain, it definitely does not pass the horizontal line test. So for this to pass the horizontal line test, we have to restrict part of the graph. So to do that, in class we decided that the part that passes the horizontal line test goes from here to here. If you want to make a note, one more time, we are restrict to pass horizontal line test. If you fold your paper in half, like a hot dog, the long way, it'll be a nice crease, and it'll kind of make a nice spot for the next graph. So the next graph that I draw will be right above that crease line. So let's draw or sketch that restricted piece. If you'd like to count the same number of boxes, I'm counting 3 boxes up to put 1, 3 boxes down to put -1, and then maybe 3 boxes left and right for -pi/2 and pi/2. And there's really no importance to that, it's just how I'm choosing to use my space. And the reason I chose these values was because if I look, the restriction is right here at pi/2, 1, passes through 0, 0, and then here, -pi/2, -1. When we draw this graph, we want to be super exaggerated with our curve. So what I mean by that is I'm going to go out of my way to really make sure that when I sketch this right now, it's super curvy. And we can label these points. So this was -pi/2, 1. Here we have 0, 0. And then pi/2, 1. This is our restricted sine of x graph. Let's talk domain and range. So the domain of this restricted graph, if I look at my x values here, it's -pi/2 to pi/2 with brackets. And then our range, if I look at my y values, goes from, this should be a -1, -1 to 1. Stay above that line. -1 to 1. So we have pulled out that restricted piece and we're focusing on it. We've talked algebraically how an inverse is switching x and y and solving. But in terms of a graph, inverse means reflecting over. So it's still switching x and y. That hasn't changed. But in terms of how to sketch the graph, we will be reflecting over y equals x. So to see what that's going to be, just so you have an idea of space, we're going to be putting two more graphs in the bottom. So if you want to take your paper and fold the bottom half in half, you'll get nice spacing. For the remaining two graphs. So in this next box, I'm going to see what this is going to look like. To be able to see that though, let's actually sketch what we just did. So I'm literally going to sketch the exact same graph. That we just did. Remember to be very exaggerated with your curve. That's a little too exaggerated. All right. So we have resketched the restricted part. Let's now sketch what y equals x would look like. So literally, think back to like Algebra 1 days. And approximately, we don't have to count exact boxes. The diagonal is right here. That is the sketch of y equals x. If you have a color, it would be good to go get it. I'm going to be using orange. We are going to now see what this looks like when we reflect the graph over the y-axis. So when we do that reflection, it's going to share this point, and this part of the graph will literally flip to the other side, almost like if you folded it in half across. What would it look like? It would come here. Like so. So what we just sketched is the reflection over y equals x. The orange piece, oh, sorry, hold on. The orange piece is what we're going to keep. So scrolling down to that last area, let's see what we're going to do. Remember, we talked about how with inverses, we're literally switching x and y. So my y values for my original graph went from -1 to 1. Those are now going to become the x values for the inverse function. -1 to 1. And I actually don't want to go that far out. For me, I'm going to go 3 boxes again. So here's 1. And and -1. Kind of just keeping in line with how I went 3 boxes before. And then we'll have on the y-axis negative pi over 2 to pi over 2, because notice it was on our x-axis for sine of x. Those will become the y value, the x values of sine become the y values of inverse sine, or sine inverse. Again, with that concept of switching x and y, it's a little easier for you to see than I can show here, but I'm going to slide this down. We literally reverse these ordered pairs. So pi over 2, comma 1 now becomes 1, comma pi over 2. One, comma pi over 2. 0, 0 was that second ordered pair. That is unaffected. And then the last ordered pair was negative pi over 2, comma -1. That's this ordered pair right here. Negative pi over 2, comma -1 will now become -1, comma negative pi over 2. And this is where that idea of reflection, so let me move it down so you can see the reflection, is really important to understand what the shape of this is. Because just from these ordered pairs, I mean, technically I could make a table and I could get way more points. But if we keep in mind this orange curve that's created by that reflection, I know that it should look like this. That is our graph of sine inverse. Let's talk domain and range. Domain is from -1 to 1. And my range will be from negative pi over 2 to pi over 2. And that is exactly what I expected, because if I look at the domain and range of the original sine graph, the reverse, or the opposite, becomes what I need for inverse sine. So if I look here, the domain was negative pi over 2, comma pi over 2. That becomes the range of the inverse function. And then in similar fashion, the range became the domain. So the entire set of x values became the new set of y values, and same for the other set in terms of trading places. So that is sine. Let's now talk cosine. So just like we did before, we're going to start by asking ourselves, what does that graph look like? So cosine starts at 1, comes down to pi over 2, down to pi, back up to 3 pi over 2, and then up. Going to the left, comes down to negative pi over 2, down to negative pi, again from -1 to 1, because we have no effect on a, up to 3 pi over 2, and then finishes at -2 pi. And it technically does go on forever and ever and ever and ever, so we can indicate that. Now, as of right now, this graph is definitely not passing the horizontal line test, and we discussed in class how to help that happen. So restrict to pass HLT. If I start here, I can't go left, because as soon as I go left, it's going to fail. So if I keep going right, I can get to right there and still be okay. So we have identified the piece that we want to keep, and now we're going to keep it. So let's pull out that restricted piece. So it's going to go from 1 to -1. And then it's from 0 to pi. And I do need this half mark at pi/2 as part of my graph. I have some space, so I'm actually going to spread it out. I'll count every 2 boxes. So let's pull out that restricted piece. It's going to start at 0, 1, come down to pi/2, and then finish right there. It's got to stop right there. So our 3 key ordered pairs are where? Well, we have 0, 1. What else do we have? We've got pi/2, 0. And then last but not least, we have pi, -1. So here we have our graph of the restricted cosine of x graph. Let's talk domain and range. If you want to press pause real quick and try domain and range on your own, we'll see if we match. What is the domain and range of this restricted piece? Well, looking at my x values, I see that I go from a smallest x value of 0. The largest x value here is pi. So 0 to pi. Then for my y values, my smallest y value is -1. My largest is 1. So I've got my domain and range. Now that I clearly see the restriction I have to put on cosine, it's time to consider what this graph is going to look like when we reflect over y = x. Before we can do that though, let's redraw the piece of the, the graph of the restricted piece. I'm going to literally make it match exactly what I did up here. Remember to make it not like unnaturally have too much of a curve, but I clearly want to see the curve here and the curve here. Once again, let's lightly sketch in y = x. Now this one is not as, sorry, hold on. Sorry about that, guys. This one isn't as visibly obvious what that reflection is going to look like. So my recommendation is really just to first focus on if you were to fold this graph over this dotted horizontal line, the reflection will literally take this piece and send it over here. So like as I'm kind of tracing it in the air or on the paper without drawing it, I'm hoping you can see that this piece right here, if I literally took this point with the curve and had it travel across y = x, it would fall right here. So we're just going to approximate this reflection right now. It's going to be about here. Let's now take this next key point, reflect it over. So I'm literally going to travel in this direction across y equals x, and it's going to be about here. So now we have what we need to do this first part of the curve that's reflected. And then we need to reflect 1 across. So reflecting 1 across, it's going to come here. And I have my reflection. This isn't exact yet. It will be once we get some ordered pairs here. It's just to visualize the reflection. So let's label this reflection over y equals x. And now let's get a slightly more accurate sketch going on in that last area of our column. To now sketch inverse cosine, we need to be aware of what will go on the x-axis and what will go on the y-axis. So originally, -1 to 1 was on our y-axis. It will now be on, let's go here, the x-axis. And the pi over 2 count used to be on the x-axis. Now it's going to be on the y-axis. So we're now going to switch our ordered pairs. You are able to see your points up here. So for example, 0, 1 is now going to become 1, 0. So on your own, see if you can take those 3 key points and plot them, and we'll see if we match. So pi over 2, 0 is now going to become 0, pi over 2. And then if I look up there at that restricted cosine of x, that last ordered pair says, you can actually kind of see it up here in the corner, pi, -1, that's going to become -1, pi. So -1, pi. Once again, if I didn't have this visualization of what the reflection looks like, I really wouldn't have any idea how to sketch this graph. So it's really important that you practice sketching the rough reflection, because then over time, you will always recall that the shape of the curve comes like this. We have successfully sketched cosine inverse. I'm going to move this over. Let's now talk domain and range. So on your own, go ahead and do domain and range, and we'll see if we match. So looking at the smallest x and largest x, my domain will be -1 to 1. And then my range will be, let's see, smallest y to, typo, sorry. Smallest y to largest y, 0 to pi. And if I look, this is the exact reverse of what domain and range was for the original restricted cosine, which is what I expect to see, because again, for emphasis, inverse in its most basic definition is switching the inputs and outputs. X becomes y, y becomes x. All right, last one, tangent. So once again, we're going to get our general sketch of tangent. Remember that for tangent, the period is 0 to pi. So I'll actually see two periods here. Tangent can be at 0. My first asymptote will be at pi over 2, and then also at negative pi over 2. Remember that on the unit circle, when that rate of change, that slope of the radius is approaching pi over 2, it gets infinitely large. And this is going to be a really rough sketch. So technically at the quarter mark, it's a 1. And again at the quarter mark, negative 1. Kind of drew over that negative 1, but it was there. And then just for practice, we can sketch in one more period. So skip 2 tick marks. Pi. And it is actually good to make sure we sketch more than one, because tangent does go on forever and ever and ever. I could literally continue to sketch these in both directions for an eternity, and I would never be done. So as it is right now, it's no good, because it definitely does not pass the horizontal line test. So let's see. How are we going to restrict to pass HLT? Well, I am completely 100% okay for all of this. But as soon as I go to, in any way, maybe say, can I use a part of a period to the right or the left? I can't. Because if I were to draw a horizontal line through, it would hit more than once. So I have identified where I need to restrict tangent to. So just like we did with sine and cosine, let's take a moment to actually just draw the restricted part. So we have a asymptote at pi over 2. And negative pi over 2. Zero. There we go. Let's talk, so let's label it restricted tangent of x. And now let's talk domain and range. Take a second on your own and see if you can tell me domain and range, please. When I come in from the left and the right, I see I definitely cannot be at negative pi over 2, but this graph will approach it infinitely without ever crossing. So parenthesis, negative pi over 2. And then when I come in from the right, I see the same. This graph will infinitely get close to pi over 2 without crossing. Now for the range, when I come in from the bottom, I hit an arrow. And when I come in from the top, I hit an arrow. So I know that's negative infinity to positive infinity. We are now ready to consider what this graph will look like when we reflect over y equals x. To do that, though, we need to redraw our graph so we can see it. So it's gonna go, take a second, I'm literally just redrawing exactly what we just drew. And then once you have that drawn, let's sketch in what y equals x would look like, and then visible y equals x. Okay. So let's reflect one piece of this, even though it's like one continuous graph. I'm just going to focus on this bottom part first. So when I reflect this bottom piece, it will send it, well, actually, before I do that, let's consider what's going to happen. Nope, sorry, never mind. Let's reflect this bottom piece. So when I reflect this bottom piece, it's going to look like that. I'm literally reflecting it over that y equals x. It's going to come up, and then I'm going to reflect this branch over y equals x. It's going to look like that. So this is a rough visualization of that reflection. So now we know the general shape. Let's get a little more specific. So this was reflection over y equals x. Let's now finish with a little bit more of a concrete graph and points. So first I need to pay attention to the fact that I used to have, and this was what I was about to kind of say at the same time when we were drawing the reflection, we do have to account for a change in our asymptotes here, because we originally had vertical asymptotes, but now negative pi over 2 and pi over 2, sorry, hold on.